you, Kobus. Yeah, and welcome everyone to our session on design for the city of the 21st century. Maybe quick show of hands. Who's in the construction industry here, just for us to get a feeling about how? Okay, that's about half. Good. So we will have a little background included to explain, first of all, why we're on a technology conference and what it is that we're doing with it and how we believe it's relevant. So maybe a little background. We are a firm of 550 architects and designers. We are working worldwide, and we design everything that you will need to build a city. So that starts with bridges to airports and railway stations. We do museums. We build convention centers, schools, universities, everything from an opera house to a football stadium, from an office tower to a central business district, and from furniture to entire cities. And the reason why we're here today is because we believe that we need a lot of technology to build much more of this. And how much of that we need might be surprising. So over the next 25 years, we will need to build new cities for 2 billion people. Yeah? And if you take the US for comparison, that's building the entire US 6 times over with every nut and bolt and house and dock shed. Or if you take India, that's 4 times that. If you take the Bay Area, including San Jose, San Francisco, various bridges, that's 240 times over in 25 years. That's about the time when I intend to retire, so I will see most of that. And the challenge is not so much global population growth in here, so you will see that we will plateau at around 10 billion. Very soon, it's urbanization. So to get the world into a work-sharing society, people need to communicate, and that's essentially why we chose to live in cities when we left hunting, gathering behind us. And if you see where urbanization needs to happen, it's, interesting. It's predominantly in parts of the world that are catching up. Yeah? So everyone wants to get where Japan, the US, and Western Europe is, around the 80-85% mark. And the growth, China is now above the world average, which is about 56%. India has to catch up, and not even on that graph is sub-Saharan Africa, which will be the biggest future growth region. China needs cities for about 200 million still. India, 300 million, that's all in the next 25 years. And sub-Saharan Africa, in excess of 600 million during the remainder of my professional career. And the challenge with that's all new cities, right? So it's not including a single building that will need to be replaced. Lifetime of a building between 20 and 40 years, so you can add 1 billion or buildings for 1 billion people on top of that. 2 challenges, feasibility and perhaps surprising identity go with that. Feasibility, just around, or maybe to use Jensen Huang's word, we are resource limited on our planet. The construction industry is responsible for 40% of carbon emissions. That's about a quarter of it, a fifth, a quarter of it in building the buildings. And then 2/3 to 4/5 in operations. Buildings are brilliant energy sinks. Yeah, they leak energy left, right, and center. And they're not built in the smartest way in most parts of the world. The other challenge is identity. So this is a shot of the urban sprawl somewhere between Shenzhen and Guangzhou. This didn't exist 30 years ago. Yeah? So these are completely new built cities. And the metropolitan area in the Pearl River Delta is now between 90 and 100 million inhabitants. And it's pretty much happened within a generation, right? In order to get there, you needed to resort to cookie cutter designs because design is expensive. Yeah? So there are not enough architects and designers, or you cannot pay for enough architects and designers to design all of that. And there's a massive opportunity using AI to adopt designs to make them homes. Yeah? So in order to deal with this massive challenge, we need better and also cheaper design. We need clean materials and circular construction. And we need sustainable urban cities that haven't been there before. This requires parametric modeling toolkits, enabling us to reuse ideas without necessarily copy-pasting them left, right, and center, the use of AI. This requires real-time data and metrics visualized for designers to ingest as we design these massive environments. And it requires integrated design to production stack and industrialized production. And because if you see how the construction industry works, it's 13% of global GDP, and it's an entirely manual industry, right? You can use the biggest computer you want. At the end of the day, there will be a guy with a piece of paper on the construction site putting it together with their bare hands. So there's an enormous potential that could be leveraged if you could streamline the pipeline from ideation to production to be remotely where most other industries are. We already use a lot of compute and AI today to solve design problems, not necessarily fabricating problems, and we also do that at large scale already. Yeah. And if you look at the way we design offices already, there's a lot that you can do with AI and compute already. So this is Mr. Allen. He came up with the Allen curve in 1970 at the MIT, and basically says that the efficiency of communication and collaboration drops significantly with distance between humans, and this has a massive impact on how we should be designing offices. So you can basically say that anything above 30 feet means you cannot really communicate efficiently anymore, and any building would want to be in the sweet spot there. And if you think about cities being communication engines and office the place where that communication happens for the purpose of our economy, that is something that should be at the center of every building design. Unfortunately, when you run the math on it, and you can do that quite efficiently nowadays, thanks to real-time compute on GPUs, you find out that most buildings work not very well for that purpose. Yeah? So this, what we showed on the previous slide, is actually proximity. So that is in response to the Allen curve parameters. You can then overlay that with different parameters such as human comfort, its orientation, like no one likes to sit in a corner, no one likes to sit to the back of an audience. And that essentially means that the buildings we design today, like the typical high-rise building with a core in the middle, about 65% of the space is used efficiently, and 35% is actually stuff that doesn't really cater to what you built the building for in the first place, which is communication and IP generation. Yeah? So we can say that the building as we know it is a subject that we could improve drastically without reinventing a single kind of technique in structural design. We could just build 35% less of it, or better, and reduce the mass of our cities just by looking at the efficiency of the layout of our buildings. And what we can do nowadays with real-time GPU compute, so this is code that we've been porting to CUDA, we can now give designers real-time feedback whilst they model their buildings on parameters like communication efficiency, human comfort levels. That's, I think, switching to yellow at the moment, so that's the comfort graph. So we can intuitively kind of get real-time feedback on the quality of the spaces that we design, and you see that this also works with organic shapes. And if you just look around here, like no one sits in a corner, you might as well not build it and save a lot of material in the course. And this is a double-digit optimization potential you will hardly find in any developed industry. But if you have real-time algorithms doing that, you can also use reinforcement learning to automate that. Yeah? So if you take the problem of where to place a core in a building or what shape a floor plate should have to work for the purpose of a building, which in the case of an office is communication, you can actually build solvers that crank out hundreds of thousands of options and optimize for certain parameters. Yeah? And that results in forms that are very different from the kind of building that you see in a typical CPD. Yeah? So in this case, this is a study we did for an office tower. It's the headquarter of the Chinese mobile phone manufacturer called Oppo, and we're building this in Shenzhen now. And the sweet spot of the different parameters, which were mostly about team organization and communication in the building, was a shape like this. What you see here, we do not build what doesn't work for that purpose. Yeah? So it looks a bit like a Swiss cheese. It's very airy, it's very light. So we have voids in there and daylight in there that contributes to quality. And we can organize teams according to the kind of social network graph of the company quite efficiently on those floor slabs. Just quickly show you how this looks like. So this is how it will look like. It's perforated. It has much less material than a building. It's lighter through that, and it's actually coming up. So hopefully soon we can see and get some metrics in return on how that works. Yeah? Or here, this may look like a standard building from afar, but if you look closer, this is the building that we finished in Beijing. These are all photos. These are not renderings. With a very similar methodology, we figured that we can actually, it's a bit more expensive to move the cores to the periphery of the building, but we get much more efficient communication in the building in return. And by providing those metrics, we were able to convince our client to go for this rather unusual approach. And what we have in the center, where you typically have a core that you cannot see through, is a 200-meter tall atrium. It's the tallest in the world at the moment. And that means I cannot only look across my floor plate. I'm in an organization. I can look 16 floors down and wave to someone there. So I have a much more kind of present state within my organization and can basically work in a dense urban situation like in a kind of medieval marketplace where I can see what everyone is doing. So it has massive benefits to communication within organizations. Or we can use computer graphics and accelerated compute for layer optimization of large buildings. So this is a good example where we can optimize buildings for commute times, pedestrian commute times. And to give you an idea, this airport is in operation since 2019, and the task was to generate a single terminal that can handle 72 million passengers per year. The reason why the desire was to have a single terminal is because in a normal airport you have APMs, automated people movers, it's these little trains going back and forth, and if they break, the airport stops. Yeah? And if you are able to get all of that under one roof and everyone can walk everywhere, you solve that problem, yeah, or you take that risk away. Yeah? And we optimized, like with very similar algorithms, the geometry for walking distance. So the maximum distance or the two remotest gates, 600 meters, 15 minutes walking works. And if you look at the capacity of this is almost on par with LAX. LAX is about 80 million passengers per year, so within 10% of that. LAX has 9 terminals, and here we get it into one single building, about 700,000 square meters. Vishu.
Yeah, thank you. Yeah, so what are we doing in a tech conference? So we can look at what the technology stack we are using to power all of these buildings. Nonetheless, historically, technology at Zaha Hadid Architects has been in the service of the user experience. But we use a zoo of softwares from borrowing from various industries, not only AEC, but looking at gaming, looking at movie and animation industry to create our buildings. And this creates a lot of source files and also a lot of multi-format files. We are one of the few architectural companies. We also borrow from the animation and gaming industry. So we borrow this Autodesk Maya for modeling, specifically polygon modeling, which is very intuitive for our designers to model and iterate quickly. And that's the reason why we use it. So in that sense, you saw the gamut of software we use. So when we were also already taking a look at universal scene descriptions, and when Omniverse and Alliance for OpenUSD was created, it was natural that we jump onto it. So with all the APIs of the NVIDIA Kit app, we were able to create our own version of that application for both geometry creation, but also for geometry delivery. What Omniverse enabled us was to create a repository of geometry and toolkits in bringing all of them into one location. So these toolkits has multiple domains in geometry processing, digital and robotic manufacture, environmental simulations, data visualizations, and AI. So diving a bit deeper into each of those aspects, looking at geometry kernel. This kernel is called ZSpace. This is a kernel we have been developing for like the last 10 years, looking at both content creation, where we are borrowing from into like geometry processing and computer graphics, looking at robotic and digital manufacture, but at the same time developing tools for later stage delivery of the project, looking at geometry optimizations or rationalization for manufacture, the sequence of construction, etc. And in the middle section is where we are borrowing technologies from the gaming industry, looking at game tech and platform design, which we will touch base in a bit. So the research borrows from multiple institutes, specifically looking at architectural geometry and our corresponding. We have collaborative setups with corresponding institutes which look into that, like TU Vienna, where architectural geometry group, looking at ETH Zurich, where block research group is, and also Carnegie Mellon, so on and so forth. So when we started looking at USD, we were looking at what are the native connectors. So there were native connectors for Maya and Unreal, but we had to build our own custom connectors where they were not available, or if the vendor is still in the process of making them. So in this case, everything in Magenta are custom connectors we built. So in this case, connecting to McNeil Rhinoceros, we built our own connection. So what this has enabled is, because we build our own connectors between the various platforms, it's simple as just copy pasting from one platform to another. So you can just take geometry from Rhino and paste it in Maya, or same thing you can do from Maya to Omniverse, so on and so. It becomes very easy for the designer to navigate between the various platforms we have in the office. What this has enabled, we have tested these workflows across multiple project scales, starting from small scale pavilion projects to larger scale stadiums and infrastructure projects to even master plans. As with all technologies, we start with like some small technology demonstrators to look at how to showcase a proof of concept. And in this case, Triatus was a proof of concept we wanted to develop not only for USD, but for other things as well. Typically, we do these kind of small-scale projects to test technology because they become the beacon for making it into commercial projects. Typically, distance between a research project and the commercialization is typically, from our experience, has been about 5 to 8 years. So in this case, we were looking at concrete and try to make it sustainable. These two words generally don't go together if you know about concrete, but the main objective of the project was to showcase the sustainability aspects of concrete by reducing the material, how to showcase that it could be recycled and reused. So how were we doing this? So this was done through an integrated design to production pipeline between designers, engineers, and fabricators. So the pipeline here you see in pink are all the design procedures, which were interspersed with engineering feedback, and the gray parts are the fabrication-related feedback. So in this case, we were using USD as a data aggregator. You can see on the right, the design procedures were all captured into the file format. So every step of whether it is structural analysis, fabrication-related information, or design procedure were all captured. These are all sequential design decisions we make in an architectural project, and it was important to capture them and embed them so that we don't lose that data. It also encodes the slicing of the geometry and eventually the print file, which is sent to the robot. All of that captured in one single file. Apart from that, we're also looking at NVIDIA CUDA for GPU acceleration. In this case, slicing of the geometry, which might take up to 120 seconds on the CPU, is now accelerated to 2 seconds on the GPU. But you could also see that this is not a simple slicing in the Z, but multi-planar slicing. Each of the planes is actually perpendicular to the force flow, which is going to experience in the final design of the bridge. What this enables, because you are perpendicular to the force flow, is to minimize and deposit material only where it's required. This also got rid of the requirement for using steel reinforcements. So this is pure concrete and no steel reinforcements to keep it in place. Such technologies, because of that integrated design to fabrication, is enabling us to minimize single-use false work. Like if you have experience in doing concrete, first you need to build the scaffold and then do the casting. And the scaffold, if it's single-use, becomes waste. So because of the integrated pipeline, we were able to minimize the number of single-use scaffold and try to use as much as reusable steel docker decks to build the bridge. What this material separation, I said there was no steel reinforcement, but there was steel at the anchors. What that enabled was material separation and what we call as design for disassembly. So you can disassemble the bridge once its use case is done and reassemble it somewhere else. So you're showcasing reuse of the same components again. But at the same time, you can also, because it's materially separated, you can reuse. So this was, again, in 2021, we did the first version of the bridge, which was for the Venice Biennale. It was there for like 6 months. Then it was easier to crush and repurpose it to a new bridge. It's a more permanent bridge at Holcim. So we reused 80% of the material which was done on the first version to build the second one. So moving on into larger scale up projects, how we are using Omniverse and USD in larger scale projects. In this case, what it's enabling is like intra-team collaborative working within ZHA. So we have people looking at landscape design, facade, structure, roof, etc. And all of them have their own preference of software. We saw the zoo of software we were using. Some are interested to do it in Rhino, some in Maya, some in Blender, some other softwares, right? So what this is enabled, USD as a file format has enabled is for the designers to still continue using the software of choice, but create an aggregator in Omniverse where someone like at the project managerial level is just looking at that master file. What this setup enables is to do quick and multiple iterations whilst being aware of the other scopes. This is going on quickly, in this case, looking at facade design, but whilst being aware of the structure, or looking at a cable net roof of a stadium whilst being aware of what it's going to latch onto. It's not only intra-company, it could also collaborative studies with the engineers, in this case, looking at structural studies with SBP, looking at various topologies we as designers are wanting to explore, and at the same time getting feedback of what are the structural performance of each of those typologies, and then you can choose the best one. In this case, also looking at can we press play on the video? This is a roof of the stadium. I'm not able to play the video. I think it's not working. Are you able to press play there?
Just move the mouse pointer to the slide, and then there should be a bar, and then in an ideal world you can press play. Nope. I think we need to skip that.
Okay.
Anyway, what you would see there is a real-time solver for geometry optimization. So we can, when interacting with the design model, use compute resources in Omniverse to planarize the panels. So these are quad panels, so they by definition are not necessarily planar. The difference between a planar panel and a curved panel in construction is a cost factor of about 10. Yeah, so you have a quite complex multivariate equation to solve to get your panelization into shapes that you can feasibly build. And with GPU compute, we can solve these problems in the space of 10, 15 seconds. And that means we can run an enormous amount of iterations over shapes that with traditional technology would take literally weeks to assess.
But yeah, I think the PowerPoint is stuck, so it may not be going.
Can we advance still, or is it all crashed now? Can you still advance the slide?
No.
Ah, there we go.
Yeah. Yeah, so the other aspect of the geometry optimization is that we are able to capture the procedure of how the geometry was constructed as a metadata in the same file. So this becomes useful when we have to exchange geometry with the fabricator, so that they can recreate it in their own platforms with the sequence. So it's kind of like an IKEA manual of how to recreate the geometry. What this is enabling is to create like expedited delivery processes. So this is a 60,000-seater stadium, which was designed to completion in 24 months. This one is already complete now. This is showcasing the cable net roof. And another stadium, which we are working currently, it's on process to be again delivered in 24 months, designed to completion. Moving on, looking at the environmental simulation aspects. In this case, we are using SimScale to kind of do the simulations for thermal comfort and bring them over into Omniverse. So we are porting them over to Omniverse to do the visualization. What was important here was this is a theater with an amphitheater in front where there's for 1,000 people, and we wanted to capture the thermal comfort of that area. And this is how the project looks. It opened like in 2024, and you can see the amphitheater in front. At the same time, what we are also looking at is the daylight simulations for the interiors to see how daylight is being captured. And this is again inside of Omniverse, trying to visualize the daylight comfort inside the building. And the same simulation, and then it was built actual. So this is how it looks on site now after the construction. Another aspect of environmental aspect we are looking into is something called hotspot. Light concentration or hotspot is like concentration of sun rays into one particular point in the context. If you remember, there was a project in London where it was actually the hotspot was burning a car or the gate of the neighbor. So it was important to capture these things in the pipeline. What we are doing, what previously we had to send these things out into an engineer to get feedback. Previously it was outsourced. Now we can capture them in our in-house design pipeline. Previously, if it was 1 week to do one iteration, now with GPU compute, it's almost real time. You can get feedback of all the geometries happening real time. And in this sense, you can then optimize the geometry for the various solar concentrations and then rationalize the facade such that you are avoiding these kind of concentrations. And that's what's also part of the OPPO headquarters, which Niels was mentioning previously. This is the rationalized facade for it. Another aspect we kind of actively work for is kind of game technologies. In this case, we saw all of the professionally generated content for creating all of the framework. So generally, this professionally generated content is very expensive. Why? Because you need to have specialist teams to work on these things over multiple periods of time. And at the same time, it's also time intensive. You need to create all of these technology demonstrators, understand what are the drawbacks, and then plug it back into the design pipeline for the office to use. So how do we want to overcome this is to kind of integrate that with game technologies, where you are kind of creating collaborative interfaces using game tech for people to work on designs. So you can then have multiple collaborators working and also crowdsource the problem. What we are doing as designers here is to create these professionally generated tile sets, which are curated for various use cases, be it offices, residences, commercial buildings, etc. And the gameplay will enable for these combinatorics to be explored. So in this case, you can see this was a collaboration we did with Epic Games, where this is a game where people are of 4 or 8 in groups are collaborating to create a city which are varied. So previously, we identified that we had to create variation in new cities. This is one way to do it, because you can capture in a tile set the variation according to cities or based on its geographical location. What it's also enabling is to capture various mixed-use scenarios. So in this case, each program is a different scenario, and through the gameplay, people are able to build city or blocks for housing, looking at what's the density out there, so on and so forth. But the same technology can also be adapted into configurators for smaller scale projects. So in this case, the same game tech is adapted into a configurator on the web, where the end user is using these interfaces to create their own house. So this was a project called Bayabu Residences in Roatan, where the end user logs into a web interface. Oh, again, the video is not working. We are using the game tech, which is using like voxels and then putting tile sets in that. So what it's enabling is for not only the end users to create their own units, but at the same time, I don't know why none of the videos are working. In this case, also doing combinatorics of geometry to enable the variations possible, at the same time also tracking all the costs associated with that. Another aspect we are currently exploring is the generative AI. We actively use it within our production pipeline currently. In this case, looking at data sets of built projects and also renders. So this becomes the data sets we kind of train our custom LoRa's on. And these LoRa's are specific to exteriors, master plans, interiors, and graphic design. What this is enabling is to create ideations at a very early stage. So people are using it for ideation of design projects, but more importantly as a design assist tool. So it is people are able to make changes into the design in the segmentation map and generate variations of the design very quickly. Because it's embedded into our design pipelines, in this case Rhino or Maya, people are able to call these tools and create variations of the facades very quickly. So it's enabling us to do in-house renders while capturing details which are important for the client. So what this is doing is bridging the gap between the abstract models the architects are working on and showcasing what is required for the client, right? The clients are generally respond more to the renders and how it is spatially working. So this AI is enabling us to bridge that gap, make it much more faster, the process much more smoother. And it's not only necessary for clients on the physical construction projects, but also on the game side. So it's the same kind of requirement for game design as well. But more importantly, where we are heading with AI is to, with and USD, is to create design co-pilots. In this case, we saw previously how we are capturing all the sequence of steps to create the procedural geometry. So now we are hooking large language models to understand this sequence of sequential design decisions we are making, such that it can be an assist for designers to predict what's going to come in the future. At the same time, it's also looking at the sequential gameplay of the city and city master plans. So in this on the right, you can see the sequential gameplay. So we are using LLMs to kind of multi-agent LLMs to kind of understand what is the sequence of these combinatorics, so that before you release the game, you can have a ML agent to actually run through all the possible game solutions and make any updates as necessary. And it's also becoming an assist in predicting simulation results, in this case looking at topology optimization, where we, as designers at a very early stage, you don't need 100% accurate results. Even if it is 70% or 80% accurate, it's already good enough. And that's what this thing is showing on the right, that the prediction of the topology optimization on a chair, in this case, is about 60 to 70% accurate. What it's enabling is to, even though it's only 60 to 70% accurate, is to make sure that we are able to iterate very quickly. Typically, topology optimization or finite element analysis takes a long time to run. And this is enabling us to be real time and make quick design sketches to explore the design domain.
Thank you. Oh, we are almost out of time, and I think we are landing bang on target. Quick recap. We talked about how USD helps us to centralize data in a format that we can process uniformly, regardless of the zoo of authoring tools that we are commonly using in the construction industry. We talked about how that enables us to parallelize workflows which are traditionally sequential, like you have to wait for the output of one party to then start the next step of another, with everyone working in a kind of uniform data environment, and in parallel, we can put a lot of things on parallel tracks. We have mutual visibility of what is happening on the project, and that is allowing us to significantly accelerate project delivery, ultimately making projects cheaper and design more accessible. Another benefit of centralized data and application-independent data repositories is that we can then build pipelines and toolkits on top of those data repositories, which means we can now afford to build specialized tools and pipelines that are built upon USD, and we can interact with data regardless on that platform, regardless of where it has been authored. And that is particularly interesting with a perspective to AI. We talked about robotic and digital manufacturing, the enormous efficiency gains we see, how we can make buildings lighter and, most importantly, easier to recycle, because what traditionally went to landfill can now be separated and reused. And we talked about crowdsourcing design, and maybe coming back to what I said about being one of the two biggest challenges in scaling up cities is the question of identity. And this is a fantastic way to actually get input and make design more varied and create an idea of ownership and identity with places, because computer gaming is ubiquitous. Everyone has their mobile phones. I believe the average age of a gamer at the moment is x36. You have it in all parts of the world. So there's a fantastic interface to combine combinatorics and configurator-like environments at large scale with an audience of future cities. And then finally, of course, every architect's dream, compute acceleration, massive gain for us. And to maybe quote Jensen Huang again, we are time limited as architects. So we always have a finite time window. And the more we can iterate over a problem, the better the solution gets. And hopefully that then also leads to better cities. This again would have been a movie. Let's see whether we can squeeze some more out of it. No, it's just stills, but doesn't matter. We're at the end. And thank you.
Great job, guys. We're going to do Q&A. So if anybody has any questions for Nils and Vishu, I'll bring the mic over to you.
Hi. Thanks for the wonderful session. My name is Nishan. I was just wondering, I mean, we are specialized in generative AI and building large language models and VLMs in a way. I was just wondering, looking at how would the use cases of VLMs be there in this particular industry, especially because language models are known for generating languages, and how do they actually connect to the world of architecture?
Massive potential there, but that's something we're working on in the future because the primary challenge there is the training data needed. What, of course, is visually very striking is generative AI for images, and I think there's not a single architect on earth who wouldn't have played with it. But we found eventually out that this is of quite limited use if you want to derive actual buildings from it, because you are dealing on the level of a derivative, right? An image does not contain the construction logic of a building. And what is most important for architects when designing is an understanding of topology. If you describe topology, you're again in the domain of language. So we are seeking to aggregate description models of geometry that allow us to actually interact or predict topology descriptions and kind of a sequence of decisions that lead to design outcome. And there are, broadly speaking, two routes. One is, which we're doing now, is building a crawler going back over 20 years worth of data that we have accumulated. It helps if you bring this into a uniform format. So having all of it in USD makes it easier to read and understand because it's something that we can process like code in language models. And the other thing that we're doing is writing listeners that take a sequential location of the design process and basically allows a language model to identify deltas in abstract design descriptions. So I think the bigger challenge at the moment is not necessarily how we process the data, it's where we find it and how we generate it. But it's doable, and I think with an increasing awareness for the benefits that these models can generate, it will get easier to accumulate. And again, that's where open data formats come in, right? So if you have application-independent data formats that allows an industry to accumulate data across projects, across applications, it's more likely that you amass a critical mass to then make effective use of large language models. And what we see as a first application would be a design predictor. So very similar to having autocomplete. If you work in an application environment, you have a record of sequential design decisions that you take. You could ghost in or propose potential next one or two steps that you can then quite efficiently pick and kind of use to kind of complete the design that you do step by step. And I believe that's quite tangible, and we are already experimenting with that.
Well, that's wonderful. I mean, in one of the occasions in past, like we have used large language models, vision language models to generate sequence of coded text, which could be transformed back into image segmentation models. I mean, we in a way, taught the language model to generate some codes. That code could be converted back into image to do some segmentation. I believe. I mean, after hearing you, I think we might also think about training the language model to generate certain sequences that to solve this kind of problems. Maybe it's not. I think not a human readable, not something which is human readable though, but could be making more sense from the architectural world.
Yeah, I mean, yeah. Thank you.
Any other questions? Yeah. Sorry, I'm going in order of the way I saw the hand, so sorry.
Wonderful presentation, thank you. I wonder if some of the process innovation that you were discussing is highlighting opportunities for business model innovation or new opportunities, new ways of thinking about how you interact with clients or new areas of business that you might enter into with these innovations.
Absolutely, and I think it's necessary. I think most of our discipline is scared about what's coming. I think it's a great opportunity, particularly if you look at the challenge that I presented at the outset. So at the moment, like at global scale, architecture is an absolute luxury. Most people live in generic buildings that have been kind of dropped out in mass by contractors. And new business models could be, for example, for architects to curate models that then help architects or industries, basically, where there's no availability of such services, to replicate them much cheaper and bring better quality to mass construction, right? So I see the future of an architect could be a curator of training data, for example, to then develop models that allow to inform mass construction. Yeah, so I think there's a lot of scope for redefining what the role of the architect or the designer can be in large scale urban developments. I'm sure you also have ideas what could be developed.
Yeah, you could also think about the stakeholder participation. So that's, I think, very important, especially when you have to build urban cities. It's important all the stakeholders come very early on, and you need platforms to do that. And like game environments are good platforms to actually suss out the feasibilities before actually building in the physical world.
Amazing presentation, by the way. This is some crazy stuff. So I run a architectural visualization business, and there's a couple questions that I have. So ZSpace, is that your software, or is that a software that you're using?
Yeah, ZSpace is a library which we built. It's a software we built for our own internal use. It's kind of for building sandbox tools before getting deployed into all the softwares we have in the office. So it was for ease of debugging. We started developing it, and then it's now currently used in-house.
Yeah.
Makes sense. So you guys don't offer that to other companies, do you?
Back to business model, I think there's an opportunity. Yeah.
So thanks for this awesome presentation. I myself have worked with lots of those 3D tools, and to have them bundled together with USD in this way is just stunning. So I was just saying there's also responsibility, because you laid out the challenges that we are facing, and you're not going to build all of those yourself. So there's a business model and there's a responsibility where you share these tools so that people can actually use them.
Yep.
And it's awesome that you're on the forefront, and it's awesome that you have the resources to build this. But this is only going to be solved if that is being given to all the other architectures around the world at a fair price, so that they can actually work on this.
Yeah. No, fair enough. And maybe just to explain, so I would say about half of that is open source already. We have a Git repo that is accessible because we work in academia. About 10% of our staff teach at various universities around the world. That's our most important recruitment channel. So everything that we teach in academia is open source, and this is a good part of the toolkit that you've seen. It's not really ready to use software, though, because we're not software developers. So these are libraries that we then either tie into host applications or predominantly now into Omniverse. And the idea is to port it all to Omniverse so that we don't have to port every piece of code to kind of X platforms that we are using. So it's all going to be unified there. So we're doing that at the moment. And yes, I mean, as we sooner or later throw all of that into academia anyway, it naturally finds its way into the open source community. But yes, I mean, I agree. I mean, if it's about solving projects at scale, that's of course what it takes at the end of the day.
Awesome talk. Thank you so much. I have a quick question on. So you mentioned that you're trying to use AI to predict the FEA results. Can you elaborate a little bit on like what approach you're thinking, what programs you're thinking, etc.?
Yeah. So the example I showed is we already published that. It's a research paper looking at how topological optimization results could be related to local geometrical properties. So once you know the correlation between these two, you can actually just predict on the fly because of that, that's why it's not, as I mentioned, it's not like a super accurate model. It's not like 100% accurate. It'll give you like a 70-80% model. That's already good enough for early stages of design because you want to explore the domain. It's not about optimizing at that stage. So yeah, I can send you a link if you're interested.
Any other questions for Zaha Hadid? Oh, yeah.
Thank you. I also think it was a great presentation. The question I have relates a little bit to, you mentioned handing over things to constructors and making it efficient for them to continue to work. So I was curious if you could say a little bit more on how that interface actually works. So a concrete example, for example, it would be climate control of the building. I guess you can, to some extent, predict how much cooling or heating capacity you need at different parts, but how do you communicate that with the supplier of that type of infrastructure too? Are they integrated in the process, or do they get something to work with when you're done?
That depends, unfortunately, predominantly on the procurement model, and the construction industry is incredibly backwards facing. It's a bit like the Soviets building the aircraft, like where you have a design studio, Tupolev, and then like 5 factories building the same plane. That's how construction works, right? So it's very rare that we have a direct feedback loop from the manufacturer, and particularly if you work on public buildings, which is our predominant body of work, you have to dump down your information to make it procurable, tenderable. But what we then do in practice is we start to hand over data-rich models. So for example, like a lot of our work's in China. So we used to have a team to produce drawings to Chinese standards. Not very cost efficient to do that from London. Nowadays, we hand over data-rich models and methods, geometry method statements that encapsulate all of the performance data. It's a data format. And then we have local partners who understand, I mean, construction is an incredibly local business, yeah, who understand best what is required for approval, also to communicate with the local contractor community and repackage that. But we are now moving away from handing over classical construction documents to kind of data-rich geometry descriptions, yeah. Like the classical version of that is BIM. We are now working with several companies that we have established a good collaboration with and hand over way more abstract and way more agile data models. So this could be kind of grasshopper models 5 years ago, and now we move towards actually using platforms like Omniverse and integrating more and more data into these geometry descriptions. So it's a fluid process, and it has to be kind of tailor-made for each and every context that we find ourselves. So there's no kind of uniform way of doing that.
All right, I'm getting the shut it down, guys. Even though we really appreciate all the amazing participation and what an inspiring presentation, we're going to stay up here until they physically kick us out of the room. So if you want to chat with Zaha Hadid or NVIDIA people, just come on up to the front.